In the previous section, we described three types of FPGA math and analysis VIs. By the end of this module, you will be able to describe the effect of VI execution modes, throughput, and latency on FPGA math and analysis VIs. Okay, so let's take a look at VI execution modes. Notice when I double-click this FPGA math and analysis express VI, I'm able to look at the execution mode. So the execution mode you can choose either outside a single cycle time loop or inside a single cycle time loop. So let's talk about outside a single cycle time loop first. So if you're putting this function outside of a single cycle time loop, then it's just going to think of it as executing like any other function. So it's basically going to execute, and then it's going to take an input and give you the output. It might take a couple of clock cycles for it to do it, but it's just going to take an input and give you an output. Pretty simple. However, let's say you want to put that function inside of a loop, and you want to make that loop be able to run very quickly, and you want to increase the throughput of that so you can get outputs at a faster rate. In that case, you would need to put this function inside a single cycle time loop. So if that's the case, then you would set the execution mode to inside single cycle time loop. And notice that there's other things that might pop up. For example, notice that latency now shows. So there's a latency that's associated with it now of 6 cycles. Also, take a look at the way that the express VI looks now. You see there's output valid, input valid, ready for output, ready for input. And those are handshaking terminals that come into play, and we'll talk about those a little bit more later as well. So if you're looking for a higher throughput for that function, then that's when you would put it inside a single cycle time loop, and this is the use case that we'll talk about in the next couple of slides. Okay, so let's talk about the inside single cycle time loop use case. So you can think about each iteration of a single cycle time loop. You can think of that as a single clock cycle. So every iteration of a single cycle time loop is going to take one FPGA clock cycle. Okay? So most of these FPGA math and analysis VIs, when you set it to execute inside a single cycle time loop, they're multi-cycle. This means that these functions take more than one cycle to return a valid result. If you place one of these multi-cycle nodes inside a single cycle time loop, well, the function is not going to return a valid value during every single clock cycle. Okay? The throughput rate of that function and the values of the handshaking terminals that you saw will determine the clock cycles during which this function actually produces a valid value. So let's talk about what throughput and latency is. So you can think about throughput as the number of cycles between accepting a new input. Okay, so it's kind of like the number of cycles, which is kind of the same thing as single cycle time loop iterations, right? And let's take a look at latency. So latency is the number of cycles before producing a valid result for the corresponding input. Okay, so we'll talk about these two a little bit more on the next slide, where we can see it graphically what that means. So let's take a look at the context help real quick. So notice on the context help for both of these functions, we've set them to the execution mode to be inside a single time loop, as you can see near the bottom. And then in red, notice that you can see in the context help what the throughput is and what the latency is. Okay, so if you take a look at the scaled window, the throughput is 1 cycle per sample. That means every single cycle of the time loop, it can accept a new input. But the latency is 3 cycles. That means the output associated with an input is only going to happen 3 cycles later. So again, let's talk about this in the next slide, and we can see it visually. Okay, so in this slide, we're going to talk about throughput and latency a little bit more. Okay, in this case, we have the high throughput square root function, and the way that we've configured it, it's going to execute inside a single cycle time loop, and we're going to have a throughput of 2 cycles per sample and a latency of 8 cycles, as you can see in the context help. Okay, so what does that mean? So let's talk about throughput first. Okay, so here we see a graph, and on the x-axis, we see the single cycle time loop iteration. So we'll have iteration 0, iteration 1, 2, 3, 4, 5, and so on. And we'll see how this function executes relative to that. Okay? So let's take a look at the inputs. So here we see A, B, C, D, and E. Those are our inputs. And A prime, B prime, C prime, D prime, and E prime are the outputs that are associated with that input. Okay? So if we're looking at the throughput, notice that this function is able to accept a new input every 2 cycles. Okay, so notice that In iteration 1, it was able to get A, and then iteration 3, it's able to read B, and then iteration 5, it's able to read C. Okay? So that's what throughput is, how often this function will be able to accept a new input. But let's take a look at the latency and how that affects things. So if we look at the latency, it's 8 cycles. So notice that we're reading in the input A at cycle number 1, and then at cycle number 9, 8 cycles later, we're outputting A prime, which is the output associated with our input A. Okay? So notice if we were running this function inside a single cycle time loop, we're gonna have to wait 8 cycles before this function even produces its first valid output. But afterwards, it's going to be producing valid outputs every 2 iterations. So after that initial latency, we're going to get a pretty nice throughput. So every 2 cycles, we'll get a new valid output. So the way that this is implemented is these functions actually have an internal pipeline that's going on. So this is why you kind of see this pipeline behavior. Okay, on this slide, I want to talk about VI throughput latency and the way that the FFT Express VI can implement it, because it's a little bit different. Okay, so let's take a look at the context cell for this FFT. Okay, so notice the length of this FFT is 64. We also have a throughput of 4.07 cycles per sample, which right now it sounds a little bit weird, but we'll explain that. And the latency here is 228 cycles. Okay, so let's take a look at what's going on. So first, let's take a look at frame A. So what's going on is, if we look at frame A, the FFT Express VI, it's going to be inside a single cycle time loop, and for the first 64 inputs, it's going to get each input right in a row. So for 64 iterations in a row, it's going to get 64 inputs. Okay? And then if we look at the latency, it's actually going to wait until 228 cycles later for the output of each input to be output. So notice that over here, we've got 64 inputs happening at the beginning, and then you see the latency drawn there. The red line that you see there is equivalent to 228 cycles. Okay, so 228 cycles later, you start getting the outputs that are associated with those 64 inputs. And those 64 outputs will be output 64 iterations in a row. Okay, the other thing now is let's talk about the throughput. So if we take a look at the throughput, notice that frame A is able to start getting those 64 inputs, and then we go down to frame B. So frame B is actually not going to be able to start getting inputs until this function is halfway done with outputting those 64 outputs with frame A. So that's kind of what you're seeing. There's a little lag there before frame B can start getting its inputs into the FFT Express VI. Okay, so if we're looking at those calculations, it's going to be 260 cycles between the start of frame A and the start of frame B. So if we do a calculation for that for the throughput, we've got 260 cycles that are going on in between the start of A and B, but during those 260 cycles, we're getting 64 inputs of valid inputs, and that's what we see in frame A. Okay, so if you do 260 total cycles divided by those 64 valid inputs that we're getting in, we essentially get a throughput of 4.07 cycles per sample. Okay, so that's how we arrived at a seemingly strange throughput of 4.07 cycles per sample. So this was just kind of a quick explanation of the FFT Express VI. I encourage you, if you're going to be using an FFT in a single cycle time loop, to go ahead and look at the help for this function. And there are other configurations that are associated with this function, so that'd be good to read up on. But I just wanted to talk about this particular use case, just because at first it seems a little strange. But hopefully now you understand it. Now let's talk about VI latency and clock rate. So the clock rate is going to specify the maximum clock rate at which this function can compile. So if we look here on the right, we notice that there is a slide bar for clock rate, and we've moved it all the way to high. So we want this function to execute at very high clock rates. Now let's go back to that second bullet. So a faster clock rate is going to require more internal pipelining stages. Okay, so that means that latency is going to increase because there's more pipelines, and also it's going to use more FPGA resources to implement that pipeline. So if we look at the screenshot on the right, we've made the clock rate very high, so the throughput is going to be smaller, which means we're going to get more throughput, but the latency is going to be 6 cycles, so it might increase the latency here.